Hello everyone, welcome back to Diksha Karnataka YouTube channel, and you are watching Sankalp KCET 2026. So if you are someone who wants to crack KCET 2026, and if you are weak in physics, or if you want to learn more about physics chapter, then you are at the correct place. So if you have not yet subscribed to our channel, don't forget to subscribe to our channel. Share this video among your friends so that we also get some encouragement to do more such beautiful videos. Now in this series we are discussing all the chapters. Throughout the series also we will be covering previous year questions for KCET as well as JEE mains, right? So if you have seen our previous chapter, we have completed the previous chapter 1, and also we have completed previous year questions for KCET as well as JEE, right? So today electrostatic potential and capacitance, last part of the chapter, capacitor and capacitance. Today we will be exclusively discussing about capacitor and capacitance in this lecture. Now before I move forward, I just want to share our excellent result that we have achieved through our YouTube lectures. So these are the toppers from our YouTube channel videos. These are the few results. As well, there are many more students that excelled through our KCET batch that we have launched last year, and it was absolutely free. This year also we have kept our KCET batch as absolutely free of cost for everyone, and if you are watching this video, then there is a high chance that your picture will be featured in our channel next year, right? So keep on doing the hard work that you are striving for, your KCET rank below 1000, right? Now let's see the chapter detail. We have already discussed it, so those who have missed it, just for your information, we have covered electric potential, potential energy, and potential difference between potential and potential energy, potential due to a point charge, potential due to a system of charges. Also we have discussed equipotential surface, relationship between electric field and potential, potential energy due to system of charges, and potential energy due to a dipole. These are all covered in our first part. In the second part we have discussed about conductors, dielectric, right, how they behave under the external electric field, also polarization, their definition, etc. we have discussed in the part 2 of the video. And in the part 3, today's lecture, we are going to cover capacitor, the parallel plate capacitor, as well as combination of capacitors and energy stored in a capacitor, right? So without any delay, let's start with the lecture first. So what is a capacitor? Capacitor is a device that is used to store charges. So capacitor basically is a device. Device means it's like an instrument. For example, if I tell you battery can store electric power. Similarly, capacitor is a device which can be used to store charges. Its primary and objective is to store charges, right? A capacitor is a system of two conductors separated by an insulator. It's generally two conductors, okay, and they are separated by an insulating medium. It can be any conductor, but it has to be separated by an insulating medium. It can be paper, it can be wax, it can be air as well, okay. Now usually in practice the two conductors have charges plus Q and minus Q, with the potential difference between them equals to V1 minus V2. Okay, so basically they have same charges. Both of the conductors, if you see, they have same Q, plus Q and minus Q, like dipole. Okay, and there is a potential difference between these two plates, and that potential difference is important, not the actual potential. Potential difference is important, and that V we use in our capacitance, that is basically potential difference. Very, very important point. Q is called the charge of the capacitor. So this 1Q is called the charge of the capacitor, though this in fact is the charge on one of the plates. It is not the total charge of the capacitor. The total charge of the capacitor is 0. Very, very important point. A lot of MCQ questions might come, maybe in your midterm exam, maybe in your quarterly exam, maybe in your pre-board exam, that what is the total charge stored in a capacitor. They will give you a diagram, and you have to identify that total charge stored in a capacitor is 0. Whereas if they say what is the charge of the capacitor, if they don't include this term total, if they don't include this term total, then the charge of a capacitor is capital Q, or whatever in diagram whatever they will give you, that will be the charge of the capacitor. But total charge is very tricky. Total charge is 0. The electric field in the region between the conductors is proportional to the charge Q, obviously. That is, if the charge on the capacitor is say doubled, the electric field will also be doubled at every point. So if you consider the electric field between the capacitor plate, there will be some electric field from positive to negative, right? And this is directly proportional to the charge Q. The electric field is directly proportional to the charge Q. If you double the charge, electric field will also be doubled. Exact value we will determine in the later stage, but you have to remember that electric field is directly proportional to the charge. The potential difference V is proportional to Q, and the ratio of Q by V is constant. So in case of a capacitor, the ratio of charge stored and its potential difference is basically a ratio which is a constant, and that constant is called capacitance. That constant is called capacitance. Okay, the constant C is called the capacitance of the capacitor. C is independent of Q or V. This is also very, very important line, that C is basically independent of the value of Q and V, as it is V is proportional to Q. So if you increase V, Q will automatically increase. If you increase Q, V will automatically increase. So V and Q are dependent on each other. That's why their ratio is constant, and that constant is independent of the value of Q and V. This is also an important point to remember for MCQ questions. The SI unit of capacitance is farad. Okay. 1 farad sometimes can be written as 1 coulomb per volt. Okay, and it is a very huge unit. The capacitance C depends only on the geometrical configuration, shape, size, separation of the system of the two conductors, and the type of insulating medium between the conductors. So it is only dependent on shape, size, the separation between the plates, and also the insulating medium that is placed between the plates. That is very, very important point to remember. Okay, sometimes students are studying, they forget that, okay, sir has taught a lot of information, but what are all the important information that I have to remember? What are all the concepts that I have to remember? So these are the important concepts that you have to remember. From the above equation, we can see that large C, V is small for a given Q. So if you can keep the C value very large, okay, then you can keep a very large charge, but the voltage between the plates can be kept as a low value. So lower is V is a very essential part. Okay, we will see that in a while. Okay, this means that the capacitor with a large capacitance can hold large amount of charge Q at a relatively small V. This is of practical importance. So practical importance means if we want a higher capacitor, always we want to have develop a higher value capacitor which can store a lot of charge, but the potential difference across the plates can be kept as a low value. That is very, very important, and it is practically used in all of the capacitor related devices. For example, your table fan, your ceiling fan, okay, your electric motors, they all use this combination, and based on the requirement the capacitance can change. Okay, for example, electric motor, generally we require a 12 microfarad capacitor. Okay, but in case of ceiling fan, we might require a 6 microfarad capacitor. So capacitance changes based on the application. There are other applications as well. We will discuss that in a while. Now let's see. High potential difference implies strong electric field around the conductor. So if the potential difference, that is V, if potential difference, this is basically V, if high is the value of V, the electric field will also be high, right? Electric field and V are directly proportional. We know that E is equal to dV by dt or dV by dx, right? A strong electric field can ionize the surrounding air. Suppose we have a capacitor and there is an electric field. So higher the electric field, there is suppose air in between, Okay, the air will be ionized. Ionized means the electrons and the molecule, they will start separating, and they can come out of the molecule, and electrons and positive ions can exist inside these capacitor plates if the potential reaches some high value. The charges produced due to the ionization are accelerated towards the oppositely charged plate. So suppose this is positive charge, this is negative charge, electric field is from positive to negative, and we have developed, say, a positive ion and a negative electron. Okay, now negative electron will move towards the positive charge and positive ion will move towards the negative charge. Now this is very bad for the capacitor. Why? Because by doing so, the capacitor will slowly lose charges. The whatever charge it is stored inside the capacitor, that will lose. Okay, this partly neutralizes the charge on the capacitor plates. The charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. So this is called a charge leak. Okay, this is also called charge leak. Okay, and this happens because the medium surrounding in between medium, they lose their resistivity to stop for higher electric field. That's why there is a limit. If you cross that limit, there will be the capacitor will no longer be able to work, right? Now there is a value as well, the maximum electric field that a dielectric medium can withstand. It can be air, it can be dielectric medium as well. Okay, if you apply very high electric field, even dielectric medium can break apart. Okay, medium that can withstand without breakdown is called dielectric strength. This is also an important term for MCQ. The dielectric strength of air is 3 into 10 to the power of 6 volt per meter. This is a electric field. If you see, volt per meter is a unit for electric field. Okay, so if you remember, E was given by minus dV by dx or delta V by delta x. Okay, so if you see that this unit is volt, this unit is meter, so volt per meter is a unit of electric field. This is the electric field basically. Dielectric strength is basically a measure of electric field that it can withstand. Withstand means it can not break down if the electric field is below this level. If it is below this level, electric field, the charges will stay. If the electric field value crosses this limit, then charges will start leaking. For a separation between the conductors in order of 1 centimeter or so. So if the separation is 1 centimeter, then this is the limit. So this field corresponds to a potential difference of 3 into 10 to the power of 4 volt between the conductors. So this is the corresponding voltage. There is a limit of the amount of charge that can be stored in a given capacitor without significant leaking. In practice, a farad is a very big unit. So farad is a very big unit. That's why we do not use farad in our day-to-day capacitance measurement. We use microfarad, we use millifarad, nanofarad are also very, very common. Micro and nano are most common farads. In fact, in some of the higher order circuit, we even use picofarad, 10 to the power of minus 12. Right, so farad is a very big unit, and we generally use farad very less. The most common used units in practice are obviously, as I said, microfarad, nanofarad, picofarad. They are the most commonly used capacitance. And if you see in the diagram, I have shown you the common used capacitors diagram. So these are, if you I will show you one diagram. There you will see a lot of these kind of things. So if you see this kind of button, this kind of cylinders, they are nothing but capacitors. Okay, these cylindrical objects or these button like objects, okay, there are some kind condenser kind of structures as well. So these are all different kinds of capacitors that you might see. Also, if you study computer science, then in the hardware part you have to learn more about the capacitance. Now if you see, this is the most common diagram. Now if you can tell me what does this represent, mention in the comment below. So this is a very common circuit, and you will see this kind of circuit in certain places. That's what I am saying. Please mention, there may be more than one places where you see this kind of circuit. This is a special thing, that is, I will not say what it is, but I will check if you are answering that in the comment below or not. So if you see, these are all capacitors, lot of capacitors are there. Okay, some resistances are also there, different types of capacitors are there. Okay, 10 microfarad, 5 microfarad, 10 picofarad, 10 nanofarad, they are all here present in this circuit. Okay, these are diodes. We will say that in a later part. This is also a diode, some resistances are also there. Okay, so this is how a circuit diagram, these are the resistances, this is also a diode. Now this is a very common kind of circuit that where capacitors are used, right? So if you study electronics, if you study computer science, then you have to know about this circuit diagrams, you have to design circuit diagrams, right? Even if you study physics in higher level, you have to design electronic circuit, because electronics is part of the physics curriculum. So if you study physics in the higher classes also, you have to know what is the value of capacitors, how it is being constructed, what are all the uses, right? So capacitance is a very, very important part of your future study as well. A parallel, now let's look into the parallel plate capacitor. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. So two large conducting plates separated by a very small distance, that is called conductor. Now in this case, you have to remember that even though it is conductor, the charges are restricted to one side only. This is a special type of conductor because they are linked to each other. Normally if you say conductors, if you say positively charged conductor, some charges will stay over here, some charges will stay over here as well. But in case of parallel plate capacitor, all the charges are residing only on the one side. That's why its electric field is somewhat different. Now if you have seen most of the capacitors, they appear like this, right? They appear like this. There is a positive, there is a negative. So positive is generally large and negative is small. So that's how we identify if this is a positive end, this is a negative end. Now how this capacitor is same as this capacitor. Okay, so if you take two papers, just like two papers, okay, and they are like, say it is made up of some conducting material, say aluminum foil, two thin aluminum foil, in between you place a paper, okay, normal paper, and if you fold it, okay, if you fold it properly, carefully, okay, then you will get this kind of cylindrical structure. So if you open this capacitor, in between, inside this capacitor, you will find two parallel plates, and they are basically folded in a cylindrical form, so that they can have a large area. Okay, if you open this, you will find a very large area inside the capacitor. It is well sealed, so you don't try it at home with a fair precaution. But if you open this, you will find that capacitor plates are wrapped around, so that you can have a very large capacitance but in a very small area. This is a clever engineering design. The space between the plastic plates can be filled with the dielectric to increase its capacitance. This space can be filled with dielectric. It can be left open for air as well, but air capacitors generally are not used, even though most commonly in physics in this class we will see mostly about air capacitors, but in practicality we do not use air capacitor. There has to be something. It can be wax, it can be simple paper, it can be wax paper, it can be mica sheet. Okay, mica sheet is one of the most common material which is used between the capacitor plates because of its high dielectric constant. Okay, higher the dielectric constant, it is very helpful for us to build up a good capacitor. Now let's look into the derivation for the expression of capacitance. Okay, so in the region, so if you go back to the previous diagram, okay, so this, we have divided the entire capacitance into three regions. Okay, region 1, okay, region 2, and there is a region 3 which is here between the plates. This is region 3. sorry. So this is region 3, 1, 2, 3. Okay, now let's see what we are talking about. So in the region 1 and 2, the resultant electric field is 0. So if you consider the region parallel plate capacitor, region 1 and 2, okay, region 1 and 2, the electric field is 0, because whatever, suppose this is positive, this is negative. So whatever electric field, even if you calculate the electric field, they will basically cancel each other, and there will be no electric field present in region 1 and region 2. Only there will be electric field in the region 3. Okay, and so it is the resultant electric field. For positive, you can consider this to be a very large charge sheet. It is not, you cannot consider this to be a large charged conductor, as I mentioned previously. Okay, it is a charged conducting sheet. It behaves like a charged conducting sheet, because in case of charged conducting sheet, the charges are residing only in one side, whereas when you consider charged conductor, the charges basically resides on both sides. But this is a very special case. In case of capacitors, charges reside only on one side. That's why the expression is Q sigma by 2 epsilon naught, and not sigma by epsilon naught that we have learned in our previous class. So sigma by epsilon naught is true for normal conductor, but sigma by 2 epsilon naught is for capacitor plates. Okay, this is only one-sided charge, not two-sided charge. Very important point to remember. Don't get confused with this expression. This expression is for charge sheet, and that charge sheet you can apply for capacitor plates specifically, even though this is a conductor. Now let us consider that intervening medium, that is here we have only air. Okay, so the intervening medium between the plates is vacuum or air. Okay, or vacuum, right? It is either vacuum or air, both are same. Now in the region between the plates 1 and 2, the electric fields are given by between 1 and 2 means, between the plates 1 and 2 means region 3. Okay, region 3. In the region 3, what is the electric field? Now in this case, if you consider electric field due to the, let us understand this properly, so that even if you forget, you can recall that in the exam. Okay, so in this case, what is the electric field due to the positive charge? Electric field due to the positive charge will be in this direction. Clear? Electric field due to positive charge will be downward direction, right? Now what will be the electric field due to negative charge? Electric field due to negative charges attract, so it will also be in this direction. Positive charges away from, right, and negative charges towards, so this is also in this direction, right? Whereas in the outside case, when you are considering the outside region 1, say suppose for positive it will be away, for negative it will be towards. So that's why they cancel. Okay, same here as well. For positive, this is say positive, this is negative. For here, positive will be away from and negative will be towards. So that's why they cancel. So this is positive, this is negative, that's why they cancel in the outer part. But in inner part, inside the plates, both the electric fields are in the same direction. So both the electric field in the same direction means this is due to positive, this is due to negative. So if the electric fields are in the same direction, then we definitely have to add them. So electric field will be added, and as you can see, electric field is constant. Electric field is constant. What is sigma, by the way? Sigma is surface charge density. So if you take any unit surface area, whatever is the charge of that unit surface area, that is the charge density, and sigma epsilon naught is the permittivity of free space. Now we know that V is equal to ED. Now how do we know that? Because we have learned that electric field is basically delta V by delta X, right? We have already learned that dV by dx or delta V by delta X. Now in the case of capacitors, what is delta V? Delta V itself is called the voltage difference, that is V. Okay, and what is the X? X is the distance between the plates. X is the distance between the plates, so we can write this as V by D. Okay, so electric field is between the plates. Electric field is between the plates. This is the distance, and voltage difference between the plate is given by V. So this expression turns out to be V by D. From here we can write that E is equal to V by D, or V is equal to E into D. Okay, so from here we are using this expression. So from here we are using V is equal to E into D, and we are putting the value of E whatever we have calculated over here. But this is not yet over. We have to replace this charge density sigma with the actual charge. So how to do that? To find the actual charge, we have to go back to its definition. Charge density is given by total charge divided by surface area, right? Charge density is charge per unit area. Charge per unit area. So that means you are basically dividing with the total surface area to calculate the charge density. If you remember, we have discussed three different charges, density of charges in the first chapter in the Gauss's law part, right? So here if we put that value as well, we will get this as QD by A into epsilon naught. So, or from the definition of capacitance, what we know that Q is equal to CV. So if you put that value from and compare this, you will get the value of capacitance to be A epsilon naught by D. This is just a mathematics, simple mathematics. Just simplify this. Or what you can do, you can put directly this expression. You can take Q by V from here as well. Okay, Q by V. So V will be divided, so A epsilon naught will come up, and this D value will be divided. So from here you say this is the capacitance, so I know that, so this is the capacitance C. So either you use this or you can write directly from there, that is absolutely up to you. So this is the definition of capacitance. So from there we calculate the capacitance of a parallel plate capacitor. Now if you see this expression, A epsilon naught by D, does it depend on voltage? Does it depend on the charge stored? It does not depend on charge stored. It does not depend on voltage. It only depends on the area of the capacitor. It depends on the distance between the plates. Also it depends on the medium. Epsilon naught basically represents here free space. We will see that what happens if we put some other medium in between as well. So this depends only on area, the medium, and the distance between the plates. It does not depend on Q or V. Even though its definition says Q by V, once we simplify we get the final result. It does not depend on Q or V. Okay, the capacitance depends only on the geometry of the system. Very important. Geometry means length, area, breadth, etc. are called geometry, right? As well as the medium. Now what will happen if we put a dielectric medium between the capacitor plates? So as you can see here we have kept a dielectric medium. Here we have a dielectric medium kept between the plates. It's a polarizing medium, and dielectric constant say K. So if you put it here, you will see that this positive plate will attract this negative end, and the negative end will attract the positive end. So there will be some polarization. Does not matter whether it's a polar or non-polar. As long as it's a dielectric, polarization will happen automatically, and it will align itself in between the plates. Okay, so let us insert a medium of dielectric constant capital K between the plates. Then what will be the capacitance? Capacitance formula we know that A epsilon by D. Now instead of epsilon naught, it is not by mistake, this is written as epsilon. Okay, epsilon is basically what? If you remember, we have also discussed that epsilon is basically K times epsilon naught, right? Permittivity of that particular medium. So that epsilon naught that came into the expression, that is because of the in between medium. Now this is the actual formula, and if we substitute this epsilon equals to K epsilon naught, we will get that. So let me write it as C dash, because it is different than C, right? C is for vacuum and C dash is for medium. So as you can see, it also depends on the dielectric constant. So higher the dielectric constant, higher is the capacitance of the capacitor, right? Or we can say that C dash is basically K times C. So this is also very important concept. Based on that, we have seen a lot of questions coming. Also practically, it is also very, very important, because as I said, it has a lot of practical applications in real life. Capacitance is the most common used electric electric component that you have studied so far. So far, no matter whatever you have studied, capacitance is one of the most used component of all electric and electrical circuit. Electronics and electrical, both cases it is used. There will be one or two few more used component, but that we will study in later part of the lecture. A parallel plate capacitor of capacitance C1 and with a dielectric slab in between its plates is connected to a battery. When the dielectric slab is removed, keeping the capacitor connected with the battery, the new capacitance and potential differences are C2 and V2 respectively. Then, so first of all, you have to understand that there is a capacitor plate. It is connected to a battery. So when you connect a capacitor with a battery, that means whatever voltage of the battery, same voltage is applied across the capacitor. This much you have to understand. So if you are connected to a battery, the same voltage is given to the capacitor. So after some time, it will take some time to charge. Okay, it will take some time for the capacitor to charge, but after that time, okay, the voltage across the capacitor plates will exactly equals to the voltage of the battery. Okay, now if you keep the dielectric medium between the plates, okay, initially its capacitance is higher. Initially, whatever its capacitance is, C1, it is higher. Right? Now, if you remove the dielectric plate, without the dielectric plate, the capacitance is given by C2. So C2 must be lower. So C2 must be lower than C1. Okay, with dielectric, the capacitance is always higher. Without dielectric, the capacitance is always lower. Now voltage in this case, both cases, is kept at a constant because of this battery. So this is the trick question. The main trick is that because the battery is never removed, the voltage will remain same. The voltage will remain same, but the capacitance will change. Capacitance, whatever was the capacitance, that will decrease. So the charge that is stored in the capacitor will decrease, but voltage will remain same. Right? So capacitance V1 equals to V2 and C1 is greater than C2. So V1 is equals to V2 and C1 is greater than C2. Okay, clear? So this is how you answer the question. You realize the question and then answer it. This is a KCET 2023 question. So just 2 years back, not super old. This kind of question is also coming in KCET exam. And sometimes some KCET questions are coming to your board exam, which is slightly easier. Those kind of questions are given to your board exam paper as well. Now, if you want to excel at academics from offline campuses, or if you want to suggest some of your relatives after you realize that you made a mistake by joining such colleges, then obviously Diksha presents you all its offline campuses. You have to go into the link given in the description of this video, fill up the form, and our representative will contact you for any further assistance. Right? So these are the toppers from Diksha campuses, offline campuses. As you can see, we have done an excellent job in 2025 KCET exam. Now let's move on to part where we will be discussing combination of capacitor. So there are two types of combination of capacitor. First is series combination. Very important. Here we have capacitors. I will be using 3 capacitors. It can have more than 3 as well, but for now, for simplicity, I will be using 3 capacitors, say C1, C2, C3. They are connected in series. In series means connected one after another. Okay, connected one after another in a linear way, then it is called series combination. Now you have connected this across some voltage source, and because of this voltage source, it will try to send some current across this circuit. Now if you see that the voltage V is applied across all the capacitors. The voltage V is applied across all the capacitors. I have kept this part dotted, that means you can add more capacitors, but primarily we will focus on 3. Okay. Now if you have to understand that in series combination, the thing that is kept constant, that is the current. In case of resistance as well as capacitance, the current is constant. But in case of capacitance, current has no value. You have to multiply current with the time to get charge. Okay, and because current is constant, time you can take a certain time interval. So after that time interval, charge going through the circuit will be constant. So charge flowing in the circuit will be constant. Whereas voltages across this component will vary. Voltages across these components will be different. It is not directly connected, right? So directly not connected means voltage will be different for all the parts. But we also know that voltages across different components adds up to give us the original voltage. So if you add all the voltages, you will get the total voltage. So that means what? V1 plus V2 plus V3 equals to V. Okay, so this is the total voltage. Also, we know that Q equals to CV. Q equals to CV. So Q equals to C1 V1. Right? So what is the value of V1? V1 equals to Q by C1. Similarly, V2 will be Q by C2 and V3 will be equals to Q by C3. Right? Now if you replace all these capacitors, using a simple circuit, let me erase that for a while. So if you replace all these capacitors with a single capacitor, only one capacitor is there. So this is what we are trying to achieve. So the complicated circuit had a lot of different capacitors. We replace all the capacitors using only one capacitor, and we call this capacitor as equivalent, C equivalent. So this is the basically is the equivalent capacitors of the circuit. This is the equivalent capacitance of the circuit. So that means whatever current was flowing will remain same, whatever voltage was there, the same voltage will be there, whatever charge was flowing, the same charge will flow. So that means charge will be same as Q. Now here in this case, the capacitor is directly connected with the battery. So directly connected with means the voltage across this capacitor will be same as V. So the voltage across the capacitor will remain V. In the previous case it was not that case, right? In the previous case it was V1 plus V2 plus V3 was equals to V. In this case there is nothing else, so the entire voltage will be applied to this, right? Again Q is equal to CV, so here Q is equal to C equivalent into V, or we can calculate V equals to Q divided by C equivalent. Right? Now whatever we have calculated, we will put these values in place of V's. For V1, Q by C1, for V2, Q by C2, for V3, Q by C3. Okay, and here it will be Q by C equivalent. Right? Now Q will be common and it will be cancelled. Anything we can cancel, we will always try to cancel. We are lazy people. We try to simplify the maths as much as possible. Sometimes it gets complicated, but when building up a theory, we always try to simplify the thing. So this is the expression for series combination. Now if you remember parallel combination of resistance that you have studied in your class 10th, that it was similar to that of the parallel combination, right? But in case of capacitor, it is coming out to be in case of series combination, right? And as you know that in case of if it is inversely added like this, then the capacitance, equivalent capacitance is less than the lowest value of the capacitor. Okay, so equivalent capacitance basically decreases over here. Now next is parallel combination. Parallel combination is when one is connected below the other. right? This is how it is connected. Again, I will use only 3 capacitors, but the same concept can be applied to multiple capacitors as well. So this is C1, C2, C3, and entire thing is connected to a battery. Now, as you see that in case of parallel combination, the same voltage of battery, same voltage of the battery is applicable to all 3 parts. You can erase any one of the capacitor and your result will be, the voltage across them will be same, right? If you erase these 2, the voltage will be V. Okay, if you erase the previous one, it will be V, right? So that's how in series combination current remains same or charge remains same. In parallel combination the voltage remains same. Okay, now say the charge in this case will be different, because it is not going through a single path, it is having 3 different paths, so charges will be different. Charges passing through the capacitors will be different. So you have to remember, in case of series, charge is same, voltage is different. In case of parallel, charge is different, voltage is same, right? If you try to find the equivalent will remain same as the previous case. Only one capacitor, battery will remain same. So the expression for equivalent will remain the same amount of charge is passing. Okay, C equivalent, and the voltage, whatever voltage you are applying, the same voltage is applied to the equivalent capacitor as well. Now let's see what are all the equations. So Q1 equals to C1 V, Q2 equals to C2 V, and Q3 equals to C3 V. Okay, so this is the 3 charges, and in case of the equivalent, Q is equal to C equivalent V. Okay, so these are the all charges. Now we also know that because of the conservation of charge, the total charge must be equals to Q1 plus Q2 plus Q3, right? So we have to put these values in this equation. So Q is equal to C equivalent into V, Q1 is equals to C1 V, it is C2 V plus C3 V. Okay, so V is common, it will be cancelled, so C equivalent equals to C1 plus C2 plus C3. So as you can see that in this case, when you connect capacitors in parallel, okay, the total capacitance increases. The total capacitance increases, right? Do not try this at home. I will tell you something, that do not try this at home, but if you can, you can try it, but not with something with live wire. So be careful if you are trying this at home. Do not try with the live wire. Switch off all the currents, all the main circuit, then you can try it. So when we used to have ceiling fan, okay, ceiling fan slowly rotate slowly after time. Over a time, if you have a old ceiling fan, it will start rotate slowly, because the capacitor which is attached to it slowly loses its capacitance and it start to rotate slowly. So once I did what I did, I learned about this in my class, and I parallelly connected 2 capacitors. Okay, I had 2 capacitors like this. So what I did, I had 2 wires, I identified which one is positive, which one is negative. It is written on the capacitor, so be careful. That's why I'm saying no, do it only if you understand what I am saying. So you connect positive with positive, negative with negative, and then you connect it with the fan's connection. Then what will happen, you will see that the fan will start rotating faster, because the total capacitance of the circuit is increased now, and that's why the fan will rotate faster. But that will also reduce the lifespan of the fan, because you are actually operating more than required capacitance of the capacitance specified for the fan, so the fan might get burned. Okay, so that's why, as I said, do it if you have a very old fan. Okay, and if you have a spare capacitor, it can be a table fan, it can be a ceiling fan. In case of ceiling fan, definitely you have to take precautions. In case of table fan, you have to remove it from the right connection, then only you can try it. Very careful, and you have to check everything, positive, negative, etc. Then only you will be successful. Otherwise, I will suggest you can go to some electric shop and ask the electrician to show it to you. They will show it to you. Okay, very interesting experiment. Now let's move on. Now let us look into this question. An electrician requires a capacitance of 6 microfarad in a circuit across 1.5 kilovolt. Okay, a large number of 2 microfarad capacitors which can withstand a potential difference of not more than 500 volt are available. The minimum number of capacitors required for the purpose is. So very interesting question. So as you can see that we require 6 microfarad capacitance total, that is the equivalent capacitance, final capacitance of the circuit must be 6 microfarad, and the power rating or the voltage rating of the capacitor should be 1.5 kilovolt, whereas the capacitor which is available to us is 2 microfarad, but very important is that it can withstand only 500 volts. So some of you might think that if I have we have 2 microfarad as a capacitance and 6 microfarad is our target, so easy question, we need to connect 3 of the capacitors in parallel to get the desired voltage, right? But that is not the case. Unfortunately, in this case, just let us understand why this is not correct. This configuration will not work, because in this configuration the maximum power this configuration can withstand is the parallel combination. So in parallel combination voltage remains same, so 500 volt, 500 volt, 500 volt, so each of them will have 500 volt, and the total voltage it can withstand will also be same, that is 500 volts. So if you have remembered that just few moments ago I have done the derivations for parallel combination, there I have discussed that the voltage in case of parallel combination remains constant, and that constant in this case will be 500 volt, but we require 1.5 kilovolt. 1.5 kilovolt means 1500 volts. Okay, kilo means 1000, so you have to multiply with 1000, so 1500 volts. That much voltage we require. So first we have to, so this configuration will not work because of the voltage, right? So voltage will remain same, that is 500 volt, that's why that combination will not work. So first of all we have to find a combination that can withstand this voltage, then we will try to achieve the 6 microfarad combination. First our target is to design something which can withstand this 1.5 kilovolt. This is a very interesting question, design problem, we call it a design problem, right? So how can we make a circuit which can withstand 1.5 kilovolt? Answer is easy. In series combination, if you have remember, in series combination the voltage gets added. So here we have to combine 3 capacitors in series, right? So that the total voltage becomes 1500 volts. So this one will be 500, this one will also be 500, this one will also be 500. So combined all 3, the total voltage this circuit can withstand is 1500, right, or 1.5 kilovolt. So the total voltage this combination can withstand is 1500 volt, that is 1.5 kilovolt. Now is the combination, is the required capacitance is 6 microfarad in this case? So here we are combining capacitances in series. Don't get confused with resistance. This is capacitance, it is different, right? Now here I will teach you some shortcut tricks so that you can solve similar questions quickly. If there are n number of capacitors, each of same value, say C, connected in sorry, there are some issue happening. So each of them are having the same value. This is very, very important. They don't have different values, but they have the same value. Okay, if they are connected in series, then what is the equivalent capacitance? The equivalent capacitance in this case will be C by N. the equivalent capacitance in this case will be C by N. Clear? Similarly, if you have n number of capacitors connected in parallel, if you connect n number of capacitors in parallel, then the combination will have N into C, that will be the total capacitance. Okay, if n number of capacitance connected in series, total capacitance C by N. If n number of capacitors connected in parallel, total capacitance N into C. So this is a very small trick but very helpful trick, especially for such kind of questions where the capacitance remains same. So here we have how many capacitances? 1, 2, 3. 3 capacitances. Each of them having how much capacitance? 2 microfarad. So what is the capacitance of this one line? This is single line, right? So what is the capacitance of this single line? That will be 2 by 3, right? Microfarad. Okay, microfarad is common, so that's why I'm not writing it. So the equivalent capacitance of this one line is 2 by 3 microfarad. Now you have to, now what you have to do? Now you have to take such combination and connect them in parallel. Parallel combination in capacitance, it increases the capacitance. Series combination in capacitance, it decreases the capacitance, right? So what we have to do, we have to connect more such capacitors in parallel, so that the we have to connect some of them, okay, so that the capacitance now increases and we get the value 6 microfarad. Each line will have the same capacitance, which is 2 by 3. Now suppose we have connected n such combination. We have connected n such combination in parallel to increase their capacitance to get our desired value of 6 microfarad. That's why it is a design problem. Even though the question looks simple, it's slightly tricky, mathematically easy but conceptually tricky. If you understand the concept, it will be very, very helpful for you in future questions. Now here we have same capacitance connected in parallel, right? Same capacitance connected in parallel, each of them have capacitances 2 by 3 and n number of them are connected. So what is the total capacitance? The total capacitance will be n into 2 by 3, right? N into 2 by 3. So this is the number of this number n, right? Now what should be our target capacitance? Target capacitance should be 6 microfarad. Target capacitance means the final capacitance of the system. That should be 6 microfarad. So from here we can calculate n equals to 18 by 2, which is equals to 9. Now 9 is not the answer for this question. Be careful again. So it has a lot of tricks. So 9 is the number of capacitances, number of this line connected in parallel, right? So 9 of such combinations are there in parallel. So what is the total number of capacitance? Total number of capacitance is number of lines times each line has how many capacitors? Each line has 3 capacitors, right? So total number of capacitance required in this case is 27. So 27 is the answer. This is a very tricky question but very interesting question. We will solve this question once more for you in our PYQ session. So don't forget to check that out. And also, if you have not yet subscribed to our channel, you are just coming and casually watching, then don't forget to subscribe to our channel. Also join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Now let's see another portion, which is energy stored in a capacitor. So energy stored in a capacitor. So what is the meaning of that? So when you are charging a capacitor, the capacitor is storing energy, right, by storing the charge. Now whenever you are storing the charge, what happens is that initially zero charge, zero work done, but as you are increasing the potential, you are doing some work. Not you actually, it is a battery who is doing the work, okay? Battery or whatever component that you have used to charge the capacitor, that device is doing some work to charge the capacitor, right? So that work that you are doing inside while charging the capacitor is basically stored in a form of energy, right? So basic definition of energy: whenever you are doing some work, if it is conservative field, that work is getting stored and you are getting some energy. So energy stored in a capacitor is basically the energy that you supplied it while you are charging it, right? So how can we calculate that? So initially, suppose both the capacitors were charged, say some inter between value of Q dash, and this was minus Q dash. Okay, final value will be capital Q, and it started from 0. So this is the intermediate value. We always take intermediate value because sometimes it is helpful for us to do some integration or differentiation. Especially in case of integration, intermediate values are very helpful, right? So this is Q dash and this is minus Q dash. Now what you are doing, you are trying to take a minus delta Q or minus dQ. Let me rewrite it. Minus dq, you are trying to take minus dq from negative plate to positive plate. That is being done by the battery. So minus dq charge you are transferring from negative plate to positive plate. So how much work you are doing? Okay, how much work you are doing? So first, how much work is done by the system? The work done by the system, small work dW, is basically the charge that you are transferring into the potential, right? VQ. I gave you the analogy last class, first class of this chapter, that like in case of electric field and charge, if you multiply electric field and charge, you get force. Similarly, if you multiply potential with the charge, you get the work done, right? Now this much work is done by the system. So how much work you have to do? You have to compensate it. So work done by you, which is basically stored as energy, is basically negative of the work done by the system, that is dq dash into V. Okay. Now if the capacitance of the capacitor, is C, then we know that Q dash equals to CV, and for convenience, let me denote it V dash so that you don't get confused later on. So let me write this. This is an intermediate voltage, that's why I'm writing V dash. So Q dash equals to C into V dash. So what is the value of V dash? So V dash is nothing but Q dash divided by C. C is constant. We have seen that. C does not depend on Q or V, right? So C is a constant. So now we have made it a integrable format. This is an integrable format, so we just need to integrate it. So what is the total energy stored? Total energy stored, U, is basically integral of du, right? Or integral of Q dash by C dq dash, or 1 by C integration of Q dash dq dash from 0 to the charge Q, right? From 0 is initial charge when it is uncharged, and Q is the final charge, so you are charging it. So I already told you how to do the integration. This is called definite integration. So definite integration, you have to do the simple integration first, x dx. So this is the format of x dx. In case of x dx, those who know integration, they can write it in one line. Those who don't know integration yet, I am telling you the value is basically q to the power 1 plus 1 divided by 1 plus 1. Okay, 0 to q, and if you put the value for 0, it will be 0. For q, upper limit first, so it will be C into Q square by 2. You will learn this with time. If you have not yet learned it, don't worry about it, but it is a very easy derivation. Anyway, Once you learn the integration, this you will say, oh my god, that was so easy. Yes, I know some student struggle right now because integration is not covered in some of the colleges. It is covered in some of the colleges as well, I know, but most of the colleges, it maybe they are following the guideline given by the state board. So in that case, this may not be covered yet, but it will be covered. Integration will be covered. In that point, it will be very simple, very easy for you, because you will be doing much harder integration in mathematics. Okay, so this is one of the forms. Now if you use this Q is equal to CV, if you put Q is equal to CV in this equation, one of the C will be cancelled and you get U is equal to half CV square. Okay, so Q is equal to CV means C square V square. So one C will cancel, so you get half CV squared. So this is the most common form. This is the most common form of energy stored in a capacitor. Okay, and it can also be written as, what is the other forms? All the forms are same, and another is half Q into V. You can write this as well. Okay, so these are all the energy stored in a capacitor. This is the total energy. This is the total energy. Okay, now energy density is a special quantity. Energy density is basically total energy divided by the volume of the capacitor, total volume, A into D. Okay, if you solve it, you will get this derivation is not part of the syllabus, but the formula is. So this is a formula where you can calculate the energy density stored in a capacitor. It is half epsilon naught E square. E is the electric field. So basically it tries to show you that the energies that is stored in a capacitor is basically stored in the electric field. The energy which is stored in the capacitor is in the form of electric field. So you are basically generating an electric field, and that electric field is basically storing the potential energy. This is a conceptual question. Based on this might be one conceptual MCQ that might come also in future. If you study physics, this concept will be very, very helpful for you, even if you study electronics or computer science. There is a question in the figure. Charge on the capacitor is plotted against potential difference across the capacitor. So charge of a capacitor is plotted. So this is the charge, microcoulomb, and this is the voltage. So Q and V are plotted in a capacitor. Okay. The potential difference across the capacitor. The capacitance and energy stored in the capacitor are respectively. So first of all, you have to calculate the capacitance. Secondly, you have to calculate the energy stored in the capacitor. So first, what we will be doing, we will be finding the capacitance. How to do that? So to do that, first of all, you have to check the values which are known to us. So for charge 120 microcoulomb, the voltage is 10 volt. For 120 microcoulomb, the charge is 10 volt. So from here we can calculate the capacitance Q equals to CV, right, or C equals to Q by V. So what is Q? Q is 120, and what is volt? Volt is 10, so it will be 12 microfarad. So 12 microfarad is the capacitance of the capacitor. Now what is the energy stored? Here we will be using the formula energy stored is half Q into V. This formula we will be using. This is easier for us, direct calculation. If you put half CV square against CV square, etc. So Q is given 120, V is given 10. So multiply, so you'll get 60, so it is 600 microjoules. Now remember, energy has a unit joules, so it will be 600 microjoules, 12 microfarad. So correct answer option C. So this kind of questions are also very common. I think this came in your board exam, not in KCET exam, but this question came in your one of your board exam. Okay, or I think it is given, maybe it is given in your question bank, okay, board question bank. I am not sure, but this is a very interesting question. Now this is the homework question. Try to answer this question and mention the correct option in the comment below. I will try to reply as much as possible, right? So check the answer, write the answer and comment down in the comment below. And to get the PDF of this lecture along with all such questions or along with all the notations and this homework question, you have to download the PDF, and for that you have to join our WhatsApp channel. The WhatsApp channel link is given in the description, and it's absolutely safe. Your contact details will not be leaked, your name etc. will not be leaked. Even we are being the admin, will not be able to see your full contact details, right? So be safe. Digital space, obviously you have to be safe, and we have kept that thing on for you so that you don't get feel that okay, my personal number may get leaked, someone might call me, I am a celebrity. So that will not going to happen through this WhatsApp channel, right? So your celebrity status will stay hidden. So work done in carrying an electron from point A to point B is in electric field. The potential difference VB minus VA is. So try to answer these two questions and mention that in the comment below, right? And I will be back with the PYQs, KCET PYQs of the same chapter very soon. Till then, bye, and obviously don't forget to subscribe to our channel, share with your friends so that we can gain the subscribers, which is very, very important for us. That gives us the encouragement to make more and more meaningful videos for you. Thank you. Bye.